That's not auto.
Okay. Let's continue where we left off. We were talking about enzymes, how great they are as analytical tools. And we stopped at explaining a coupled reaction. A coupled reaction, just to remind you, is that you need two enzymatic reactions to get to a spectrophotometric analysis. So we need enzyme 1 and enzyme 2. The measuring reaction, because we're measuring this substrate, and the indicating reaction, because we're measuring the absorption either of reactant or a product. So we talked about, we need to consider pH optima of the enzyme. So when we design a coupled reaction, we want to make sure that the enzymes we use don't have very different pH optimum, because we don't want to keep changing pH in the system. So we'd like to have or select enzymes that both of them have a pH optimum of 7 or 6 or whatever it is. Also, we will make sure that this is not a rate limiting reaction, the indicating reaction, meaning it's not a slow reaction. So if our reaction is about 30 minutes, we want to make sure that this reaction, it happens as soon as P1 is generated, P2 is generated right away, and an absorption is measured. Okay, so these are the two main cautions or considerations that we have to keep in mind when we design a coupled reaction. So if I ask you a question, what are the two main concerns or cautions when designing coupled reactions? These would be these two. Okay. We talked about this example, the glucose as a coupled reaction. Another example is measuring ethanol. So measuring ethanol is you need dehydrogenase enzymes, two of them. One is alcohol dehydrogenase, where NAD plus takes hydrogen from the alcohol to generate acetaldehyde. And then another dehydrogenase, but it is an aldehyde dehydrogenase. So it will take hydrogen from the aldehyde. So in this case, we're measuring absorption of NADH. So you can see here we're generating NADH twice in the reaction to enhance the sensitivity of the reaction, basically, because ethanol might be present in a small concentration. So when we do the calculations, 2 mole of NADH produced would be equivalent to 1 mole of ethanol present in your sample. Okay? So when we apply enzymes in analysis, it's either to measure the substrate or constituents, or we are after measuring an enzyme activity itself in a food product. So when we're measuring constituents, that means we care for the substrate concentration, and like we talked last time, we want it to be first order or zero order with respect to substrate. Think about order of reactions. I don't have my candy today, but still, some of you really need participation points. So when I'm measuring substrate, do I want my enzyme reaction without looking back to your notes? I mean, I don't mind looking at your notes, but I would like you to think about it logically from what you know about reactions. So if I'm concerned about substrate concentration, I want to detect substrate concentration. Is it first order or zero order?
It's first order.
First order. So you want the reaction rate to be dependent on the enzyme concentration. That would be first order with respect to the substrate. You do not want to design your experiment where there's an abundancy of your constituents in there. You always have to dilute it in such a way that your concentration is much lower than Km. Where a change in concentration, you will see a change in rate. You will see a measurable change in your absorption. So you can back calculate your concentration of the constituents you're measuring. Okay? So examples, application, sulfite. You know, you have to report sulfite on the label because of people with sulfite sensitivity. So that's a common measurement in certain food products. We talk about that later in a different chapter. But you can get assays to determine sulfite concentration using enzymes. Glucose, we talked about that. Starch, you hydrolyze with alpha amylase, glucoamylase, and then you get glucose and you use enzyme to measure glucose. Back calculate the amount of starch. D-malic acid, so if you have apple juice and you want to, you have a government check, they want to make sure that your apple juice is authentic and doesn't have any synthetic products, they would measure D-malic acid because the natural organic acid in apple juice is L-malic acid. So presence of D-malic acid will indicate synthetic product or presence of synthetic product in your apple juice. So now flip the coin. Here we are measuring enzyme concentration, so we do not want the substrate to be limiting. So these are all terms that I'd like you to know what I mean by limiting. So it's limiting the reaction. We do not want the substrate to be limiting the reaction. So I want the substrate to be present in abundance. So here, my reaction to the substrate will be first order or zero order.
Zero order.
Zero order. So zero order because you put the substrate in abundance, so any change in enzyme concentration, and that's what we're measuring here, enzyme activity or enzyme concentration, will elicit a change in the rate, will elicit a change in your absorption, so you can measure activity. So you want your substrate to be in abundance, so your reaction will be first order with respect to the enzyme, not to the substrate. So examples, peroxidase is commonly tested for what application? In processing.
Is it for off flavors?
Okay, you could, but there is to test efficiency of a processing step. You measure, huh?
Is it pasteurization?
What?
Is it pasteurization or is it?
It's not pasteurization, it's blanching. Have you heard of the term blanching? So you blanch to inactivate enzymes, and peroxidase is the most, peroxidase and lipoxygenase both are thermally stable. So if you test one or the other and they are inactivated after blanching, that means your blanching process was effective. But lipoxygenase we also tested in products where they could be present naturally and impact lipid oxidation. So if we care about that, we measure lipoxygenase activity. Alpha amylase, it's an indication of if it's present in high amount, let's say in flour from wheat, that's an indication that you're hydrolyzing your starch in the flour. And by doing so, you have lower viscosity in a product. So it's a measure of quality of the flour, an indirect measure of quality of the flour by determining alpha amylase activity. Some people don't measure it directly. They measure something called falling number. Have you heard of this term? Falling number? You did not come across anybody? No? So a quick method to determine the starch and the amylase activity in your flour. So you will put flour and water in certain proportion in a kind of graduated cylinder, and then you have a plunger, and then you monitor how fast your plunger moves a certain distance in your graduated cylinder. That gives you an indication of the viscosity of your starch in the flour. So the higher the alpha amylase, the falling number will be higher. The plunger will fall lower in your graduated cylinder. So it's an indirect measure of alpha amylase activity and potential hydrolysis of starch in your flour. Rennet. So, like I said last time, rennet activity is measured to determine how much rennet you need to add to a certain amount of milk to create a certain amount of curd in a particular amount of time. So it's important to determine that in your rennet ingredient when you obtain it for cheese making. Okay. Often you have biosensors that are enzyme based, where you have your enzymes immobilized. For example, we have something called glucose electrode, and the electrode has an immobilized glucose oxidase. And when you immerse it, it has also an oxygen electrode. So you have an electrode that has the enzyme immobilized, and then it can also detect changes in oxygen level. So you can determine the glucose concentration by putting that biosensor in your solution. It measures uptake of oxygen as the glucose gets oxidized by glucose oxidase. Another example is urease immobilized on an electrode, and urease is inhibited by a pesticide. It is present in
Is there another example? Like I heard in lactate milk, do they have immobilized lactase to
determine the amount of lactose.
Not determine, but just hydrolyze the lactose. Is that what they are using in the lactate milk?
Oh, so immobilized with different application. Here is to detect a presence of constituents, but immobilizing lactase is another thing, a processing aid to remove lactose from milk, converting to galactose and glucose. This is a processing aid application. Here's an analysis application. Yeah, but both are immobilized. You're correct with that. Okay, so yes, so the other example is urease, which is an enzyme that gets inhibited by a pesticide. So if the pesticide is present, so it's a detection method for presence of a certain pesticide, which is the organophosphorus pesticide. So if it's present, then the urease will be inhibited, and then it won't act on a certain substrate, or you won't get a certain detection. So to sum up, examples, we test alkaline phosphatase in milk to test pasteurization. We talked about that. Rennet for cheese making, cereal products, alpha amylase. Fruit juices, we want to inhibit pectin methyl esterase to maintain the cloud in your orange juice. So we determine the activity of the pectin methyl esterase as a quality check. Peroxidase to determine blanching. Lipoxidase can be done to determine blanching efficiency. I have the corn here. I'm trying to remember why. It could be high fructose corn syrup. Yeah. High fructose corn syrup, you actually you break down the starch to glucose, and then you use invertase to convert glucose to fructose. Yeah, okay. All right. That's it for the enzymes. You can shift gear and start pH and titratable acidity, which is the subject of your lab next week. pH and titratable acidity. Often there's a common mistake that people use them interchangeably. And I've seen that quite a bit when I was looking at your project summaries. So you say pH, measure pH, and then you put the method as titration method. Or measure acidity and you put the method as pH meter. They're two different things. Okay? Anybody wants to volunteer the difference before we look further into the notes? Difference between pH and acidity. Nobody. I'm sure you know this. It's just you're nervous to say. Lynn, you want to say, I feel it in your eyes.
Oh no.
Okay. We'll move on. We'll explain as we go. So, what is true about organic acids or organic acid that could be present naturally in a food? Bye, Sarah.
I forgot something for work and I'm like, I have.
That's okay. Goodbye. Tehu? What's that? You feel bad? Good. We will miss you too. Tehu? All of the above. Okay. Why is the organic acid can buffer at multiple pH? Tehu? Since you said it's all of the above, you're stuck. I don't expect you to know. That's fine. Although you might have come across it. Claire is thinking about it. Go ahead.
I'm not confident anymore, never mind.
If we think of citric acid and acetic acid, do you know from your organic chemistry, I don't know if you take that in organic chemistry, do you know what's the difference between citric and organic in terms of carboxyl groups? No? So citric acid has 3 carboxyl groups. Acetic acid has 1 carboxyl group. Carboxyl is your COOH, yes. So buffer, that means your COOH or carboxyl group is going to give a proton to buffer. So if you have 3 carboxyls or 1 carboxyl, you're going to have 3 different dissociation factor versus 1 dissociation factor. So you will have 3 pKa's to 1 pKa, right? And then the optimal buffering capacity is that when the pH is equal to pKa. So if you have 3 pKa's, you get the organic acid can buffer at 3 different pHs. Because you have 3 different carboxyl groups, and each carboxyl group will have a different dissociation factor. Okay. And because they are weak acids, they have good buffering capacity. All right. Let's think about that one. Mallory, is that yes? Is that true?
I would think it's true.
Did we say pH is the same as titratable acidity? No. You could have 2 drinks, same pH, different titratable acidity and different sourness. Titratable acidity is the total concentration of your acid, whether it is dissociated or not dissociated. So false. You will know more as we go with the lecture why. All right, so titratable acidity, we're measuring total acid concentration. Total acidity, it affects flavor and it's an indication of maturity. So take fruit, for example, grapes. You start with high concentration of acid and then you will have more sugar. So as the grape mature, you will have less acid, more sugar. pH, it's a measure of the hydrogen ion. When you have hydrogen ion coming from an acid, combine it with water, you get hydronium ion. So this is a measure of the active hydrogen, active acidity, basically. And it doesn't relate directly to flavor. It impacts reactions in food, such as what kind of reactions? Okay, Claire? Enzymatic reactions, because different pHs will, enzymes require different pHs to work. So you will impact enzyme reactions. What else you will impact? different pHs, you will impact
What's the shelf life?
microbial growth. And also it will impact what processing, what thermal treatment you need to do to pasteurize, if it's acidic food or non-acidic food. And another thing, other chemical reactions can be impacted by Makia. We're dropping as flies. Okay. Other reactions, for example, disulfide linkages can occur with high pressure, high temperature, and high pH. So you can impact chemical reaction, enzymatic reactions, microbial growth. Okay. So here's why an example of when you have same concentration, different pH. Same concentration of an acid, yet different pH. If we look at HCl, it's a very strong acid. When we say strong acid or weak acid, it really is how readily it's going to give its protons. Okay? So the dissociation factor is really high. So it's fully dissociated. It's a strong acid, it's fully dissociated, and then when it's fully dissociated, your pH is really low, about 1, when you have 0.1 normal HCl. Whereas acetic acid, it's a weak acid, so you have a dissociation of 1 to 3% usually. So you have your acid mostly not dissociated and a little bit dissociated. Okay, so that's the arrow, a blue thinner than the red. Okay, so it's mostly in this. You have very low concentration of free or active hydrogen. So therefore your pH at the same concentration will be 2.89 compared to 1. Okay, so we have a lot of calculations ahead of us. Calculations based on concentration. So you probably are all familiar with molarity, right? Number of moles per liter of solution. You're familiar with normality too? You're looking at me blank. What, are you familiar with normality?
Chelsea sort of explained it when she was lecturing because it came up during the protein section.
Okay, so you are familiar. So the answer is you are familiar with normality.
Probably only a little bit though.
So normality is number of moles or mole equivalent of solute per liter of solution. So what is a mole equivalent? So if we think about acid-base reaction, so you have hydrogen in acid and OH in base. So the transfer of hydrogen or OH, or the number of hydrogen or OH that can be transferred or exchanged in a neutralization reaction per liter. So 1 molar H2SO4, it has 2 hydrogens. So the number of mole equivalent is 2 because it has 2 hydrogens, so it can exchange 2 hydrogens. So 1 molar equal to normal because normality equals number of mole equivalents times molarity. Okay, so if we're talking NOH, 1 molar of NOH equal how many normal of NOH? 1, because you have 1 OH. All right. Equivalent weight is also important because if you have H2SO4, the equivalent weight of H2SO4 is the molecular weight divided by the number of mole equivalents. So the molecular weight of H2SO4 is 98, so equivalent weight is 98 over 2 is 49. It's important when we learn how we calculate titratable acidity. So we are going to use equivalent weight because, like I said, if you're calculating total acidity when you have citric acid, would be different if you're determining total acidity when you have malic acid, for example. Citric acid will have 3 carboxyls, malic acid will have 2 carboxyls. So when you at equilibrium, you have to take into account what are you exchanging, 2 hydrogens or 3 hydrogens. So that's why we need, when we're doing these calculations, we take into account the equivalent weight because it depends on how many hydrogens or OH minuses we're exchanging. We'll get back to that when we talk about calculation of titratable acidity. But I'm introducing what you will be using in terms of calculations. Percent concentration, you're all familiar with that, is either weight per 100 ml or 100 grams, grams per 100 grams, or milliliter per 100 milliliters. So it's the ratio of weight or volume of the solute to the weight or volume of the solute plus solvent multiplied by 100. So you're all familiar with the percentage. Concentrations can, when we have very low concentrations, so we don't necessarily report them in percentages, we report them in parts per million, which is milligram per kilogram or liter, or we can say micro. Oh, we lost Sam too. Bye, Sam.
Red lights dust.
What's going on? I'm gonna leave too in a minute. Just walk out.
Say you're sorry and walk out. Sorry.
You're so discouraging. So ppm, you can also see it as microgram per milliliter, and then there's parts per billion, becomes microgram per liter or kilogram, parts per trillion, nanograms, and so on. As we go lower in concentration, we use parts per million, billion, trillion. Okay. Equation of neutralization, why is this important to us right now? Because titratable acidity, we are titrating with base, right? So we are base titrating the acid in order to determine total acidity. So the way we calculate is basically milliequivalent at neutralization or at equilibrium. We have milliequivalent of one reactant equal milliequivalent of the other reactant. And the milliequivalent is volume times normality equals volume times normality. Are you familiar with this term? NV equal NV or MV equal MV. Are you familiar with that? Okay. So we can use the same principle for dilution protocols. So if I have a stock solution, I want to prepare 0.1 normal HCl using my stock solution, which is concentrated 12 normal HCl. I want to prepare 1 liter. I can use this equation to determine how many milliliters of 12 normal HCl I want to dilute up to a liter to get 0.1 normal HCl. So pull out a piece of paper and hold on to it, because this is going to be over 2 lectures. And start calculation. That's a good time to leave.
What?
For me to leave.
Oh,
That's
right
a good
now?
thing.
Yeah. I'll be like, what?
Go ahead. Do the math. What do I do? Does it go down?
Yeah, you can.
Yeah. Oh. It was bothering me as well. Maybe it's a good time to give plus 10 to everybody.
You can give Sarah's 10 points to me.
Okay, so did anybody come up with anything? Katie, what do you do with that 8.3? Correct, but what do you do with it?
Because you're done the equation.
No, but when you're actually trying to prepare a reagent, I'm gonna go with Riley. I know you, Billy.
I just bring to volume,
With what?
some water.
Yes. So you get, okay, here's what I would like you to write in an exam question. You have an exam this coming Monday, don't you? It's going to be all new questions. Okay. So, I lost my train of thought. So if I ask you, you don't just calculate and you write 8.33 milliliter, which is true. You just say we get a volumetric flask, a 1 liter volumetric flask. I put some water in there, add my 8.33 milliliter of acid. It's always safer to add acid to water rather than water to acid. And then I make up to volume to the mark by distilled water. And then I get my 1 liter of 0.1 normal HCl. So complete it. In chemical reactions next semester, you're going to actually be preparing the reagents that you will use in your experiment. In food analysis, you come in, everything is prepared for you. Chemical reactions, you're going to be preparing reagents. So it's good that you not only calculate, but also know what to do with it after that. So here it is, you just apply the equation and you get 8.33 milliliters. So pH, it's simple, you all know this. Acid is a proton donor, base is a proton acceptor. So acid will form a hydronium ion and base has hydroxide ions. So in neutralization, acid plus base give you salt plus water. So hydronium ion reacts with hydroxide ion to give you water. So the concentration of hydronium ion by the concentration of OH minus or hydroxyl will give you the ion product constant for water, which is at 25 degrees C, is 1.04 times 10 to the negative 14, and that's your range of the pH, up to 14, right? So it really depends on the concentration. Your pH is dependent on the concentration of hydronium ion. But another term is POH. POH is the concentration of, is dependent on the concentration of the OH minus. So at pH 7, we have 1 times 10 to the negative 7 because pH is negative log concentration of hydronium. Okay? So the pH 7, that means the concentration is 1 times 10 to the minus 7 to get pH 7. Same for hydroxyl. So the product of these two is 1 times 10 to the minus 14, which is the ion product constant for water. Okay, let's continue on your one piece of paper. Yes, Claire.
Are we assuming that 7Up has the same ion coefficient as acid?
What's that?
Are we assuming that 7Up, we're just using the KW?
Yes, yes. Yes, we always assume that that's your pH range, 1 to 14. Okay, so go ahead, do that on that same piece of paper. Yeah, you need your scientific calculator if you have one to get the log. Okay, anybody with the first? What's the concentration of the hydroxide? Yeah?
1.59 times 10 to the negative 12.
I do have a different number. Claire?
2.93 times 10 to the negative 11.
2 point what?
93 times 10 to the negative 11.
Why do I have, it's, you're closer.
2.82.
2.82 times 10 to the minus 11, yeah. So basically you take this, you divide it by this.
Oh, I think, I don't know, at least what I did was 1.04 times 10 to the
Yeah, on the slide before.
Ah, okay, so if you use 1.04, then yes, you'll get the 2.9.
Yeah.
Yeah, yeah, yeah. Yeah. Okay, next, the pH. You have it already,
I
Mallory?
did that one first and I said.
Go ahead.
Is it 2.2?
No. What is it, Billy?
3.45?
Yes. How did you do it? Okay. Here it is. Okay. So this one, you can take 1 or 1.04 or either, then you divide it by that, you get the concentration of the hydroxide. Now for the pH, you can take the log separately. So you can do log 3.55 and get that from your calculator, gives you 0.55. And then log 10 to the negative 4 is negative 4, and then you add them, okay? So that you add minus 4 plus 0.55, you get negative 3.45, but the pH is has a negative here, so negative becomes 3.45. Well, each one can do it differently on your calculator, but this is one way of doing it separately, then adding them. Okay. So if beer has a pH of 4.3, now the opposite. So here where you want to use anti-log on your calculator. So pH 4.3, what would be the concentration? Do you have anti-log on your? You have it already? Or you're just thinking?
I don't have a calculator.
Oh, okay. Okay.
Is anti-log the same as 10 to the?
10 to the minus.
Yes, yeah.
Okay.
Yeah.
It's been a while since
Yeah, I never understood the new calculators,
What?
the new scientific calculator that you use 10 to the negative whatever. Yeah, don't have to show me, I won't even, don't bother. I learned on old calculators. Anyway, yeah, so what do we have? Anybody with a number? Okay, Brad?
5 to the negative, or 5 times 10 to the negative 5th.
Yes, okay, there it is. Yeah. That's me using old calculators. Well, as long as we reach to the final answer the way you do it on your calculators, that's fine. Okay. So, are we good, Sophia?
Yeah, sorry.
Yeah, no, but are you good with that? Or
Yeah.
why not?
No, go ahead. No, I don't want to go back.
Okay. All right. So, in the lab, you're going to use pH meter to determine pH. You're going to use pH meter to determine endpoint of titration, to determine total acidity, and just this is a very superficial introduction to pH meter. I'm not going to go into the detail that the book provides, but anyway, we are measuring with a pH meter the hydrogen ion activity, relating it to the concentration. Okay, so it's a potentiometer that measures a voltage or a change in the electric potential or a voltage at infinitesimal current. That means at a very small, tiny current. So you have a reference electrode and you have an indicator electrode. The electric potential is constant between the two. When there is an ion in the system, the ion will cause a change in the potential, and that is related to the concentration of the ion. So the change in the potential will be correlated to the concentration of the ion, and using mathematical conversions, that would be converted to a pH reading. That's a very simple explanation of that. That's all. For the pH meter, you have electrodes, reference and indicator electrodes. In the past, you had them as separate, two individual. Now they are combined in one electrode, so you have the reference as well as the indicator electrode, which is sensitive to your hydrogen ions. And some pH meter also have another probe for temperature, because pH is dependent on temperature as well. So some pH meters, you can have a probe for measuring temperature while you're measuring your pH as well. So guidelines for use, we have to maintain the probe. So basically always if you're using high protein solutions, you have to always clean it with a pepsin enzyme, for example. Or if you're using high lipid, so you do alcohol wash, or a rinse, if just a general DD water rinse. So it depends on the solution that you are using to test your pH. You want to make sure that you're properly maintaining your pH meter, following the instructions that comes with the electrode. Always we calibrate, and we use 3 pH units apart, so we can use pH 4, 7, and 10, and you can do 2-point calibration or 3-point calibration. So we always tend to calibrate, so all the pH meters will be calibrated for you for next week. And then proper storage, we store in KCl solution. Never leave your electrodes to dry. So still have a few minutes, why not? So titratable acidity, it's a measure of the concentration of intrinsic acid in food. So basically we're titrating with a standard base. So the organic acids that are commonly found in food is citric, malic, lactic, tartaric. So if you're measuring acidity in milk, you're always calculating your percent titratable acidity using lactic acid as your organic acid. If you're doing tartaric, let's say grapes, so you're measuring tartaric acid. If you're doing lemon, citric acid, etc. So the main organic acid that's present in the highest abundance in your product, you would use that to calculate titratable acidity. Inorganic acid often used in beverages, phosphoric and carbonic. Carbonic is when you have CO2 gas bubbled in aqueous, it becomes carbonic. acid. It has a real impact on your titration results, and you'll see that in the lab, and we'll talk more about it in the lab on Monday. So in order to determine the endpoint or the equilibrium where we titrate all of the present acid, we either use a pH meter to determine the endpoint or an indicator dye. So in the lab, we will continue this discussion so that we know the difference between the two, and then on Monday I'll finish up this lecture. Well, no, not on Monday. You have an exam. Okay. Since I didn't finish this lecture, the exam is up until enzymes.
Is it just between the two tests?
Oh, the exam is just where we left off last time. So we have from moisture all the way to enzymes.
We have class on Wednesday.
Okay. I know it's Thanksgiving, but we do really need to have a class on Wednesday. Otherwise, we'll be very behind. Hang on to your sheets of paper for next time.